think 4K was about the most they could squeeze in. But of course there were programs which were bigger than 4K. So this is a bit to bodge, really. But it's Intel's solution to a problem that hit them when they designed this. This was originally designed in the 1980s. It's a very old processor now. But they still manufacture it because there are now new versions of it with lots of memory inside and so on. So, I'm not suggesting that we all go out and start using classic 8051s. I think that would be a bad choice for any project in this day and age. There are much better members of the family out there. Okay. External code memory I haven't said about, but we'll do that one as well. In the 8051, the address lines which are connecting to the data memory, the assumption is they're also connected through to the code memory. So this is, and the same goes for the data. Now, technically, I shouldn't really draw an arrow that way because code memory you can't write to, so I'll just draw it like that. You could try writing to it, but there's no instruction to write to code memory that exists in the 8051. But it has its own special read signal for code memory. In fact, we've already seen it. It's this psend signal. So the read for code memory is this psend signal. The 8051 is considered a Harvard architecture because it has distinct memories, code memory and data memory. But I think you saw the slides at the start of this course, yeah?
While connecting this, these two are...
they are connected, but don't worry, it's not going to cause us a problem, and I'll explain why in a minute.
Are they separate ICs or something?
These are separate ICs, so this could be a ROM, and this could be a RAM. That could be a RAM as well if you want, but for now, just think of them as separate. They're separate memories, and the way we access them is different. Okay, and that's the crucial thing. That in the case of the 8051, when it wants to read or write to data memory, the control signals it uses are the read and write signal, which are taken from port 3.
Can you give any example of any IC?
Yeah, I can give. Yeah. A very old one that used to be used for code memory might be something like an EEPROM, like a 27128, which I think is a 16K byte EEPROM. Or you can have a 27256, which is a 32K device. 32K, 16K, whatever.
So both are the same ICs, but for different purposes.
This one's got more memory than this one. This is data memory. The assumption is you're going to be able to write to this as well. You have a special signal to write to it if you want to write to it.
Okay, but the ICs are same, like the numbers are same, right?
What do you mean by the numbers?
Like we could use it for ROM or for RAM.
It's up to you as the designer how you're using IC. So this could be a RAM, and this could be a RAM if you want to. That's up to you. The microcontroller doesn't know that. But even if this was a RAM, the microcontroller has no way to write to it because it has no control signal for writing to what it thinks is code memory. But for data memory, it has a separate read signal and a separate write signal. For code memory, there is only a read signal. Now when, for example, let's say you do, you're in the middle of a program and the next instruction, the program counter is pointing somewhere into code memory, or maybe it's pointing to EA, who knows. That fetch, provided the EA is low to say that we're going to external code memory to get the information, effectively the value that's in the program counter will automatically be presented to P0 and P2. It will be latched into here. And then once it's latched into here, P2 will stay the same, but then P7 will be brought low at the right time, and whatever's on the data will be read into port 0 and then loaded into the instruction register all automatically for you. So it's not like you are having to, you know, as the programmer, do this sequence of things. The microcontroller will do this automatically. But
sorry, invading your space.
To do this automatically, Intel assumed that you've built a system that looks like this. If you haven't built a system that looks like this, it's all going to probably go pear-shaped. So, but exactly what type of device this is and what device this is, the microprocessor doesn't know, the microcontroller doesn't know. It just assumes it's of the right type. Yeah.
For instance, if I use like 27128 for both of these,
yes.
One is a wrong, one is a right.
Well, a 27128 is always the wrong.
So for a RAM, we use it.
Well, I'll give you I'll think of an example. There's
I lost interest already.
6264,
Still
which is a RAM.
You're still paying attention now.
There are lots of different RAMs out there.
Carry on.
The crucial thing is if you use a ROM here, there is no signal to wire up to do a write for ROM. ROMs don't have write signals normally. They have a special program pin, but that's only for programming purposes. There's no means of writing to a ROM. You need a special programmer. Yeah.
Can you program to external programming through the microcontroller?
No, you can't. Well, no, you can't without a bodge. There are ways around it, and I'm going to come on to those, but I probably won't do it today because I think it'll take me a few minutes to explain. But for now, assume that as far as the 8051 is concerned, no, you can't write to program memory. But there is a fix.
I mean through like the initial, not at runtime, like.
While you're programming it.
Can you program through it to?
Well, I know of. I don't believe there's some kind of circuitry inside the 8051 that then would allow you to go through it in a kind of data chain to some external device that I went out of.
Is that good, Robin?
There are versions of the 8051 you can use some like I2C or SPI and things like that to write to some electrically erasable thing. I don't think, in terms of what you're asking, I don't think it's possible. Okay, let's recap where we are then. So the whole purpose of this very strange thing that I've been talking about is Intel's attempt to not use up all the pins on the 8051 for connecting to external data and external code memory. And Intel achieved this by basically introducing a relatively simple 8-bit latch together with a control signal for that latch. Provided you've wired things up this way, for example, if you execute the instruction MOVEX into the accumulator from 1 to 3, 4 hex.
No, yours.
Implicit in the instruction, you've told the microcontroller everything it needs to know in order to achieve this task. First of all, the X tells it it's got to go external data memory. And you've also provided the address that it needs to put onto there. So just that one instruction, if you were to put that in your code, what would happen is port 0 will get the 3, 4. Port 1 and port 2 will get the 1, 2. Now this says data memory, so it won't do anything with psen, because psen is a control signal only for control memory, for program memory. This has nothing to do with program now. Executing this, now fetching this instruction would have used program memory, but executing this instruction, we're actually going to data memory, because the instruction says we need to get something from data memory. So we've already brought the instruction into the instruction register, and now we're executing this instruction. And as part of executing this instruction, port 0 and port 2 get the address, and then we use in this case, we're bringing it from the outside world into the accumulator. So the read signal will be taken low here to activate a read to this data memory. with the correct address on the address lines. So out on the data port, effectively the data will appear, and then port 0 will take that information and it will be copied into the accumulator. And all of that sequence of actions will be done automatically just as part of executing that one instruction. Okay, there's more to be said about port 3, but I think I'll come back to that in a few slides. I'm going to put a couple of normal slides up and then we'll have a look at port 3 in more detail. So, anything else I want to say about this? Let's see how we get on. So that is the proper pinout for the classic 8051. We've actually been around every pin on here, but I haven't talked in detail about port 3 yet. The things in brackets are what we call the alternate function for these pins. And you can see that in the case of port 2, we've got a something in brackets. That means when port 2 is being used in this way, with external memory, that pin is going to become the A15 line, that's the A14 line, and so on. The microcontroller will assume you've wired it up that way. So if you decide, actually that's going to become the A15 line, and that's going to be the A8 line, it's all going to go extremely horribly wrong. This use of external memory assumes it's wired up in precisely the way I've shown. There's no negotiation there. It's that way or it doesn't work. There's the read signal for the program memory. This is the signal for controlling the latch. The reason why it's got this here is this is also used for when we're programming the device in a very special way. That's how we get to internal program memory, but forget about that. There's the EA signal, which tells us is the program memory external or internal to the device. There's port 0, and you can see it says AD things because it's both, this line here is both A7 when it's the right time, it's also D7 when it's the right time, as its alternate function. Because remember, port 0 has multiple alternate functions. Coming around here, port 1. Port 1 is the only port on the 8051 that has no special other function. Port 1 is just port 1. It's just 8 lines that you can control, and they don't do anything special. So, if you're wiring up to LEDs and switches and all that kind of stuff, port 1 is usually the best place to start. There's the reset. There's port 3 that I'm going to go into in more detail later on. There's the 2 pins for the crystal. There's the reset, the VCC and ground. So that's all the 40 pins. I will say something more about port 0. Almost time for a break. Port 1, 2, and 3, they can actually drive quite a bit of current. They have enough, the transistors in them are such that, if you like, they can provide current to drive an LED without problem. But port 0 is a bit bizarre. Port 0 normally is wired up like this. So in the case of well, first of all, this is ports. Let's do ports 1, 2, and 3. In the case of port 1, 2, and 3, things are wired up more or less like this. So this is somewhere else. This is the CPU controlling this transistor. So when this transistor is switched on, effectively this pin will go low. And when this is switched off, then it's pulled up by this internal resistor. In the case of port 0, things are slightly different. So that's ports 1, 2, and 3. If I draw you the diagram for port 0 as an approximation, it looks like this. Looking pretty much the same so far. There's the ground. There's the pin, and that's it. Whoops. There is no internal pull-up resistor. Now, The reason why I'll put that in as a dashed line, because when you're using port 0 in its alternate function to access external memory, that resistor does exist. But as soon as you decide you want to use this port yourself, you're not using it to access external data memory, that's effectively disconnected, it's not there. It's what we call, it's called an open collector output. And that can be useful in certain types of circuits. One example might be, you can do something where, for example, you might wire this up to 7 volts here through a pull-up resistor. So now when this transistor is switched on, it goes to ground. When it's switched off, the voltage is pulled up to 7 volts. So it allows you to connect the microcontroller to devices that don't use 0 and 5 volts as their high and low, but to other things. That's just one example of why we might want to use open collector. But I'll come back to it in a couple of weeks anyway, but I just wanted you to be aware that when Intel created this device, they didn't create all the ports equally. Go you first.
Can you explain a bit more about a pull-up resistor? Because I have seen that normally push buttons and switches are connected with this pull-up resistor.
It just means if you had a switch into a device, such as a microcontroller, and you just leave it like this, well, the question is, when it's open like this, what's it going to read? I mean, it's floating, as you said, the technical term is floating. It's not connected to anything. So what we would normally do in a situation like this is we might build a circuit more on these lines, where when it's unconnected like this, this resistor, effectively, you can either think of it as a small current flow this way, or you can think, basically it's connected to this VCC. And so if you sample this point here now, it's effectively, there'll be a small voltage drop across here, but it's almost at VCC. It's no longer floating. But when you close this switch, now depending on the values of R you choose here, normally you choose this to be quite big, so this might be, say, 10K, and this might be ground or very close to ground, let's say this might be 100 ohms or something. Then, based on your knowledge of potential dividers, almost all the voltage is dropped across here, virtually nothing's dropped across here. This potential now becomes almost at ground. So by doing something like this with a couple of external resistors, I have a circuit that the switch is never indeterminate. It's either when it's open, this resistor's pulling it up to a certain voltage, or when the switch is closed, it's being pulled down to ground here. Now, I have to have these resistors of sufficiently large value because some current is going to flow through both resistors. And if they were both low values, I'd end up with a large current flow through it. And I also need to choose right values so that when this switch is closed, the effectively potential divider action is such that the potential at this point is almost at ground. So, pull-up resistors are there to stop things from floating. Because if I have a pin being used as an input and I haven't connected it to anything, and I sample it, who knows what it might read that as? Now, in some devices, they have an internal pull-up resistor, so that even if you don't connect it, when you read it, you'll read something meaningful. But not all integrated circuits are made that way, and some of them don't have anything. If they don't have anything, you really don't know what's going to happen when you read it. By the way, as a complete aside, the pins on here are generally considered to be TTL compatible, transistor-transistor logic compatible. When they're being used as inputs, any of these ports, effectively, this is a digital device. So when you read an input, effectively for something to be reliably read as a 0 coming in, it's around about less than, certainly less than 0.5, and it's probably closer to about 0.3 volts. So if you want to have a pin that's being used as an input, and you want it to be read correctly as a 0, you must make sure the potential on that pin is lower than about 0.3 volts. Now, it might be a little bit more, a little bit less, but it's that kind of value. Conversely, if you want to read a pin, and it's a logic 1 that you want to read in, well, what kind of voltage constitutes logic 1? Well, if it's TTL, logic 1 is usually anything above about 2.4 volts. So less than about 0.3 is 0, above 2.4 is considered logic 1. So if this pin here was at 2.7 volts potential relative to ground, and you read it, it will read as a 1. Now you might say, okay, what happens if it's between 0.3 and 2.4 volts? If you're in that range, it's not, Intel don't promise to tell you what it will be read as. Will it be read as a 0 or a 1? So as a designer, you try, using TTL things, never to have voltages appearing on pins in the range 0.3 to 2.4 volts. That would be bad, because in that range, when you read it into the microcontroller, we don't know what it's going to read as. Is it going to be treated as a logic 1, or is it going to be treated as logic 0? Right, it's 5 to 10. We'll take a break for 10 minutes. So at 5 past 10, we'll carry on with our run around the pins. We've still got a few slides to go, just a couple. And then we're going to get on with some assembly language programming.
Sweet.
So stretch your legs. You might just be able to get a quick coffee.
Oh, yeah. Robin, no homo. Yeah, still sleeping, dude.
Yesterday.